So imagine finding like an old college notebook belonging to one of the greatest living mathematicians in the world.
Right, Terence Tao.
Exactly, Terence Tao. So you open it up to this dizzyingly complex proof, and there, scribbled in the margins in this really frustrated handwriting, are the words, "I hate Jean Bourgain," followed by just a massive all caps AARGH.
Yeah, that messy, intensely human frustration is just, it's incredibly revealing.
It really is.
And strangely enough, it represents the exact quality that artificial intelligence is, well, it's on the verge of stripping away from mathematics entirely.
Yeah, and welcome to today's deep dive. We're looking at a deeply thought-provoking essay that was published in August 2026 by Terence Tao.
Based on a lecture he actually gave at the International Congress of Mathematicians.
Right, and the mission for our conversation today is to explore this really profound shift. We're looking at how the imminent arrival of advanced AI is forcing the mathematical community to, radically rethink not just their daily workflows, but what the actual fundamental goals of mathematics even are.
And Tao frames this whole dilemma around what he calls the community response question, which
That's the
is
sociological part.
exactly. What's fascinating here is that he's not actually asking a math question. He is asking a sociological and ethical one. Like, how does a community of human thinkers respond when their defining task, the very thing that gives their profession meaning, can suddenly just be outsourced to a machine?
Okay, let's unpack this, because for you listening, I actually want you to think about your own profession right now.
Yeah, that's a good way to look at it.
Think about the daily tasks that define your specific expertise. What happens when the tools you use get so powerful that they force you to ask why you're even doing the work in the first place?
It's a scary thought.
It is. And to understand the gravity of this AI moment in math, we actually have to look backwards. Because the essay points out that mathematics has faced this sort of existential crisis before.
Right, the ghosts of math past. To really comprehend why mathematicians are taking the current AI shift so incredibly seriously, you have to look at the period from roughly 1900 to 1930. Okay.
Tao refers to the centuries prior to this as an era of naive foundations.
Naive foundations.
Yeah, mathematicians were doing brilliant work, proving theorems about sets, numbers, concepts of infinity, but they hadn't rigorously defined what those foundational things fundamentally were.
Oh, I see.
They basically just delegated the pesky philosophical definitions to philosophers and got on with the calculating.
But it feels like building a skyscraper on a swamp. I mean, it holds up fine until suddenly it doesn't.
Exactly.
And the essay mentions that the floor fell out with things like Russell's paradox in 1901 and Gödel's incompleteness theorems in 1931. Well, let's do a quick pause here because these sound incredibly intimidating.
They do, yeah.
What actually is Russell's paradox? Is that the one about the barber? How did a paradox break mathematics?
Oh, the barber analogy is the perfect way to visualize it. Imagine a town with one rule. The barber shows all those, and only those, who do not shave themselves.
Okay.
The paradox kicks in when you ask, does the barber shave himself?
Oh, wow. Wait, right. If he does, he violates the rule. If he doesn't, well, the rule dictates he must.
That's a brain breaker.
It is. And Bertrand Russell applied this exact logic to set theory, the idea of a set of all sets that do not contain themselves. It created a logical loop that essentially proved the foundational assumptions of mathematics at the time were capable of contradicting themselves.
And a contradiction in math is fatal, isn't it?
Completely fatal.
Because if 1 + 1 = 2, but also equals 3, the whole system just collapses.
Exactly. And then Gödel shows up 30 years later and makes it even worse.
Oh, great. How so?
Gödel essentially proved that a formal mathematical system couldn't simultaneously be consistent, sufficiently expressive, and capable of proving its own consistency.
Wait, run that by me one more time.
Basically, he mathematically formalized the liar paradox. This statement is unprovable.
Oh, man.
Right. If the statement is true, then math has true statements that can't be proven, meaning it's incomplete. If the statement is false, then the unprovable statement can be proven, making the system inconsistent.
Mind-bending. Absolutely mind-bending. But the discipline didn't just throw up its hands and quit, right?
No. The outcome of that 30-year crisis was that they built an explicit, rigorous, standardized foundational framework. They mechanized the rules of reasoning so that math could be conducted with absolute confidence.
Okay, so they stress-tested the framework of mathematical truth.
Yes. Today, however, Tell argues we are entering an era of comparable turbulence. Except this time, the threat isn't to truth.
What is it then?
We are stress testing the implicit framework of mathematical values. We are being forced to redefine what we consider a contribution, what we reward, and who or what we regard as having done the work.
Wow. And this perfectly sets up Tal's working hypothesis, because in most tech debates, people get completely bogged down in arguing about whether AI will ever be able to do real, creative, high-level math.
Right, that capability debate.
But Tal bypasses that entirely. He says, let's just assume a strong version of AI capability is true, and that these tools will reasonably soon perform research-level tasks.
And he has tangible evidence for making that assumption. The essay references the First Proof project.
Oh yeah, the May 2026 batch.
Exactly. Let's look at their second batch of evaluations. This was an independent assessment that took genuinely novel, completely unpublished research problems submitted by working mathematicians, and they fed them to 4 frontier AI systems.
And out of 10 completely original, never-before-seen math problems, 7 received at least 1 passing grade from an AI.
Yep, 7 out of 10.
Meaning experts judged the AI solution to be either essentially flawless or only requiring really minor revisions. And it only cost, what, tens to hundreds of dollars in computing power per problem.
Just incredibly cheap. When you look at those numbers, debating if AI can do math becomes a complete distraction.
It reminds me of planning for a meteor strike. We're spending so much time arguing, will the meteor actually hit us? And Tao is saying, look out the window. The meteor's in the atmosphere, it's glowing red hot, and it's going to make impact. What do we do right now?
And that framing forces a very uncomfortable realization. Because once you accept that the meteor is here, that AI can do the math, you have to examine what you are actually asking it to do.
Right.
If the goal of mathematics isn't simply getting the right answer, what is it?
Which, on its face, sounds almost absurd. I mean, isn't getting the right answer the entire point of math?
Historically, we thought so, but only because all the varied goals of mathematics were perfectly aligned.
What were the other goals?
Well, the discipline has always had multiple objectives: solving hard problems, developing new theories, training the next generation, and creating aesthetic works of logic.
Okay.
For centuries, doing any one of these things naturally helped you achieve the others. You struggle to solve a problem. In the process, you develop a new technique, a community forms around that technique to explore it, and eventually students write textbooks about it. Progress in one area drove progress everywhere.
So we just used solving problems as a kind of proxy metric for all the other good stuff.
Right.
You solve a problem, we assume all the learning and community building just naturally happened along the way.
Exactly. But then the essay introduces Goodhart's law.
Goodhart's law.
Yes. It was originally formulated in the context of monetary policy, actually. It states, when a measure becomes a target, it ceases to be a good measure.
The classic everyday analogy for this is a fitness tracker. Like your actual goal is to be healthy, but the proxy measure you use is 10,000 steps a day.
Right.
So what happens? The measure becomes the target. You end up sitting on your couch, shaking your wrist up and down to trick the pedometer. You hit the target, but you completely fail the underlying goal of getting healthy.
That is a perfect analogy.
And the essay implies that generative AI is basically the ultimate digital risk shaker.
If we connect this to the bigger picture, generative AI is uniquely dangerous here because of its underlying architecture. It is technically ungrounded. It optimizes for the appearance of a satisfactory output.
Right, because large language models operate by predicting the next most statistically probable word or token based on their training data.
Exactly. They don't tether their output to an objective underlying mathematical reality. They are literally designed to find the loophole between metric, giving you a sequence of words that looks like a correct answer, and the actual goal of discovering mathematical truth.
So it's giving us the 10,000 steps without the heart rate increase.
Yes.
And the AI industry is financially incentivized to optimize for those benchmarkable achievements. They want to show investors that their model solved X number of problems on a standardized test.
And the consequence is that this historic alignment of goals shatters. By hyper-optimizing solely for solving problems, the goals diverge from one another. We are entering a reality where we might generate 1 million flawlessly solved problems that teach humanity absolutely nothing.
Let's zoom in on that, because Tao uses the pipeline of problem solving as a case study to show this divergence in action.
Yeah.
If we define the goal of math as just solve as many unsolved problems as possible, it fails almost instantly.
Oh, completely. Even prior to advanced AI, simply optimizing for generating solutions resulted in a flood of noise.
Pretty quiet.
Take the Riemann hypothesis, one of the most famous unsolved problems in mathematics regarding the distribution of prime numbers. Every working mathematics professor receives a steady stream of amateur emails claiming to contain a complete proof of the Riemann hypothesis.
Wow, really?
Oh, yeah, and the vast majority are just riddled with errors.
Okay, so attempt 2 for defining the goal.
Yeah.
Solve the problems and mathematically verify them to be correct. And this introduces proof-assistant languages.
Right.
The essay mentions Lean, Rock, and HOL. I've heard these names thrown around, but what do they actually do? Like, how does a computer language verify a human's math?
Think of them as incredibly strict compilers for logic. In traditional math, a human writes a proof using natural language and standard notation, skipping minor steps because they assume the reader is an expert who can fill in the blanks. Proof assistants force you to auto-formalize the proof. You translate your logic into computable code. The software checks every single microscopic logical deduction against fundamental axioms.
Oh, I see.
It removes the need to trust the human author's reputation. The code either compiles or it doesn't.
And AI is getting exceptionally fast at writing these formally verified proofs. But the essay points out this creates a brand new, modern failure mode, which is the black box verified proof.
Yeah, Tao points to platforms like the Erdo's problems database. We're already seeing submissions of lengthy AI-generated proofs that the software verifies as mathematically flawless.
So the computer says, yes, this logic is correct.
Exactly. But the submitters, the humans who prompted the AI, openly admit they lack the expertise to actually explain what the machine just did.
It's mathematically true, but intellectually useless. No human brain can extract meaning from it. So we move to attempt 3 for the goal of math. Solve it, verify it, and ensure it can be clearly communicated. But wait, AI is a text generation engine. It spits out grammatically perfect text in seconds. Shouldn't it be amazing at this?
You would think so. It has flawless grammar, but a very mixed record on mathematical exposition. When an AI writes a proof, it tends to dwell at agonizing length on trivial, routine computational steps, while completely glossing over the truly novel, interesting leaps in logic.
It misses the point, basically.
Yeah, it fails to offer the high-level overview that tells a human reader, here's the core trick, and here's why this matters to the broader field.
And here's where it gets really interesting, because this is where that anecdote from the very beginning of our deep dive comes back.
The Bourgain paper.
Yes. Tao, studying the 1991 paper by Jean Bourgain, getting so frustrated he scribbles AARGH in the margins. The essay brings this up to highlight the concept of natural friction. In a human-written proof, the parts of the argument that the author found genuinely difficult usually retain some awkwardness. Maybe it's an apologetic remark, a sudden change in notation, an unusually careful subproof, or just a paragraph that has clearly been rewritten 5 times.
And we tend to think of that friction as a defect. We assume the ultimate goal should be a perfectly polished, mathematically flawless document.
Which is what the AI gives us.
Right. But that human friction acts as a crucial set of signposts. It signals to the reader, slow down here, this part is hard, pay attention.
Wow.
That friction is how the tacit, unspoken knowledge of a scientific field is transmitted from one generation to the next.
This completely flipped my perspective. If an AI comes in and overly polishes the text, it sands away all that natural friction. You are left with a proof that is, as Tao puts it, easy to read but hard to learn from.
Because mathematical success isn't an abstract production quota. Tao quotes the mathematician William Thurston from 1994, who argued that the measure of our success is whether what we do enables people to understand and think more clearly.
So a frictionless, hyper-polished AI proof might solve the equation, but it doesn't help humans think better.
Exactly.
Okay, so even if we somehow get the AI to write a perfectly messy, human-readable proof who is actually checking all this work, don't we run into a massive bottleneck?
We absolutely do. The final stages of the mathematical pipeline are community acceptance, which is traditional peer review, and canonicalization.
Okay, define canonicalization for me, because the essay leans pretty heavily on this term.
Sure. Canonicalization is the slowest, most deliberative stage of the process. It's when a mathematical result is fully digested by the community.
Digested.
Yeah, it gets rewritten in its most natural general form. It gets connected to neighboring theories. Eventually, it gets simplified and placed into textbooks for students. It represents the broad consensus of human understanding.
But human friction and that slow community acceptance are the actual bottlenecks. I mean, the entire academic infrastructure, the journals, the hiring criteria, the way scientists get priority for discovering things, was built on the assumption that proofs are scarce and hard to come by.
And what's fascinating here is that when you hook up an AI fire hose to that delicate human speed pipeline, you cause massive systemic shock.
Obviously.
The essay describes this as shifting from an era of proof scarcity to proof abundance, or, to use his more visceral metaphor, an era of proof indigestion.
Proof indigestion. Because if the working hypothesis holds true, the AI generates proofs much faster than humans can verify them.
Right.
It auto-formalizes them faster than humans can write them up nicely, and it will just completely overwhelm the volunteer peer review system. The system just chokes on the abundance.
But wait, isn't there a massive dark irony here regarding how these AI models were built in the first place?
Oh, the deep irony is that frontier AI tools were trained almost entirely on the output of that human canonicalization process.
Wait, really?
Yes, the polished textbooks, the carefully digested theories built over centuries of human peer review, that is their training data. So if we flood the system with unreadable, undigested AI proofs, we break the canonicalization pipeline. And by breaking it, we destroy the very data ecosystem that future AI models need to approve.
The machine relies on the slow, human consensus it threatens to overwhelm.
That is wild. I'm looking at the recommendations Tao brings up from the Leiden Declaration on Artificial Intelligence and Mathematics, which was published in June 2026.
Right, endorsed by the International Mathematical Union.
And one of the big recommendations is transparently disclosing tool use. But honestly, looking at this indigestion problem, doesn't that feel a bit like closing the barn door after the horse is bolted? I mean, how does admitting you used an LLM stop the system from choking?
Well, transparency alone won't stop the flood, but it prevents the covert flooding of the zone. It's about shifting the culture. If you use a proof assistant, you state it clearly.
Okay, that makes sense.
Tao leads by example here, actually including a disclosure in this very essay, noting he used AI for literature searches and formatting. You have to normalize transparency so people don't use these tools to generate opaque black box proofs while dodging criticism.
The declaration also argues that authors have a new obligation to support the peer review process. Because AI makes reviewing so much harder, the burden shifts to the author to provide those formal, machine-checked proofs alongside their work, rather than just dumping an AI-generated text document on a volunteer reviewer.
And most importantly, the declaration calls for affirming the humanity of authorship. Credit and responsibility belong to human beings, not automated systems.
Right.
AI might obscure the human labor involved in finding a solution, but it doesn't replace the human responsibility for standing by that solution.
Tao has a personal rule of thumb for this that I genuinely think should be adopted by every single knowledge-based profession right now.
Oh, definitely.
He says, if the authors cannot convincingly give a clear, expert-level talk on their results, a talk that proves they truly understand the underlying logic, then the result shouldn't be published, period. Even if it is formally verified by a supercomputer, a proof that no human can explain is an incomplete proof.
But implementing this requires a massive cultural pivot. Mathematics has historically operated on a theorem economy,
Right.
where prestige and rewards go to the person who is first to generate a solution to a problem. The community has to shift toward a proof digestion economy. Activities like exposition, teaching, mentoring, and rigorous peer reviewing need to become the most valued and prestigious parts of the field.
It's just wild to me. The arrival of a super intelligent calculating machine is actually making the squishy, deeply human skills, communication, teaching, empathy, community building, more valuable than they have ever been.
It forces us to remember that mathematics, beneath all the abstract symbols, is a collective human enterprise. It is not just a database of correct answers, it is the shared pursuit of understanding.
So to recap this journey, we started with the working hypothesis that the meteor is already in the atmosphere and AI is ready to do the heavy lifting.
We did.
We unpacked Goodhart's law, discovering how AI's predictive text loophole optimizes for the appearance of an answer, threatening to shatter the core goals of the discipline. We explored the vital hidden value of natural friction in human writing, how our messy struggles, the AARGHs in the margins, are actually the signposts that teach others how to think.
Yeah.
And we saw how the shift from proof scarcity to proof abundance threatens to cause massive indigestion in the academic system, ironically threatening the very data the AI needs.
But by reclaiming human authorship, demanding that we can actually explain our work, and shifting our values to prioritize digestion and teaching over mere generation, the community can survive the flood. AI isn't killing math, it's refining its purpose.
For you listening, as AI inevitably marches into your own field, whatever that may be, ask yourself, what is the friction in your job? What are the messy, human, difficult parts of your process that actually transmit tacit knowledge to your colleagues? Don't let the machine quietly sand those away just to hit a metric.
Because once the friction is gone, the learning stops.
I want to leave you with one final thought to mull over. If we are entering a world where AI becomes capable of perfectly solving and explaining every problem we can think of, will the future of human education be less about finding the right answers and entirely about learning how to ask the right questions?
The answers will be abundant. The questions will be the scarce resource.
At the start of this deep dive, we talked about how math feels like a pristine, rigid structure immune to human ambiguity. But maybe the real revelation is that the ambiguity, the struggle, the apologies, and the margins, the friction, was the concrete, holding the whole thing together all along. Thanks for going on this deep dive with us. See you next time.